I will be talking today about changing the game in the area of processing radiology text using NLP. I will be joined by my colleagues from Clemson University, including Professor Amy Apon and students Ashton, Williamson, and Dhruvisha Patel. My name is David D. Hilster. I've been 6 years in the supercomputing group at LexisNexis Risk Solutions. I'm in charge of the ECL-ID on Windows. I'm currently working on an NLP++ plugin and bundle for HPCC systems, and I have 35 years of practical experience in NLP. I'm also co-author of the computing language NLP++ and creator of visual text. And 2022 was the first year we proposed pure NLP projects for students. And because of that, I thought I'd start out with a little humor here. I felt that maybe I was leading people to the promised land of NLP, but maybe not everybody would agree. So I thought this was kind of cute. If you look down, you see this one lemming who has to be turned around and says, "I've changed my mind, please, machine learning." Or no, it says, "I changed my mind, machine learning, please." But that was kind of my feeling. Would anybody follow? But it turns out there was quite a bit of interest. So that was a good thing. Well, we know that HPC systems has changed the game in supercomputing and risk management. NLP++, which is now a plugin for HPCC systems, is hopefully changing the game in natural language processing. That's what we are trying to do. And also the Clemson Radiology project is changing the game as well. That's the intent in universities. You do research and you want to break new ground. You don't want to do what's done before. In fact, we'll have some of the students talk about that. Now, before we start, I have 35 years experience in NLP, and this is my take on game-changing technologies through the decades in natural language processing. The first AI really was in the 1940s when they were looking at code breaking, using computers to do code breaking. They thought, well, if we can code break, maybe we can code break Russian into English, looking at that, using the same techniques and using that for translation. But they quickly found out that was a very hard problem. In 1950, they talked about what computer intelligence may be in the Turing Test. We'll talk a little bit about that. In 1960, Noam Chomsky, he really is the father of modern linguistics and set us up for the rest of natural language processing for the future. Eliza in the Blocks world, which I'll talk a little bit about as well, in my opinion, was really the first intelligent program, which really knew everything about the world it was programmed for. And the linguistic rules from Noam Chomsky in the 1980s were starting to be applied because computers were more powerful. And of course, we ran into problems. I say we because we were part of that, ran into problems of combinatorics. In fact, the linguistic rules went to the ultimate, which was the programming language called Prolog, where you just literally put the rules of the language and you didn't have to write any program, and supposedly it could parse the text. But of course, it was not that successful. Machine learning and statistics really started in the 1990s, and of course, we know where that is today. And the translation really started to take off in the 2000s using machine learning and neural networks. And of course, again, we know how good that is today. It's much better. And of course, speech to text really started to take off in 2010 as a commercial, even though it was around a while. I see that it really started to take off. And what I'm going to be talking about today is the 2020s, where we are talking about writing intelligent programs. And part of that would be using NLP++. Well, the Turing Test was originally called the imitation game by Alan Turing in 1950. And the Turing Test is a test of a machine's ability to exhibit intelligent behavior equivalent to or indistinguishable from that of a human. And it's kind of interesting that it was called the imitation game. So it's kind of suspect, is it really intelligent? And it was also interesting that the test was really involving human language as the heart of the Turing test. So, and natural language processing or natural language was at the heart. So if you've probably heard a couple months ago about Google's employee who claimed that a computer became sentient after conversing with the program, well, I think they lost their job because they should have just looked it up, even Googled it, to pardon the pun. And it was really using a technology called Lambda, which responds to prompts by finding patterns and predicting sequences of words from large swaths of text. And the results can be disturbing for humans, meaning it really seems like there is another person on the other side because the conversation seems very intelligent. But in reality, it's simply an immense parroting memory that can feign intelligence using tricks. This passes the Turing test, but this is not intelligence. So it gets me to a point here where I'm going to be changing the game of the Turing test and talk about what I think the intelligence tests should be for computers. And again, this is my take and my opinion, and that intelligence tests should be: humans must be shown that a computer has understood text in the same way as a human understands it. This involves much more than just text interactions. It involves examining linguistic knowledge, memory, and world knowledge. Now, one of the first programs, if not the first program to be intelligent, I claim, is Shirley called the Blocks World. And it was constructed and programmed by Terry Winograd in 1968 to 1972 from MIT. And it had linguistic and world knowledge and logic of the blocks world. You can see a little picture here. And it could explain itself. It could even ask questions. You could even ask it questions why. It would even understand that your question wasn't clear. Pick up the big red block. Okay, grasp the pyramid. I don't understand which pyramid you mean. So there wasn't a question you couldn't ask about this world. So it understood everything. And in my opinion, even though it was a small blocks world, it showed you that if a computer can understand everything about that world, it can be really intelligent about that world. It also got me thinking about what is programming. If you're going to talk about intelligent programming, well, what is programming? In fact, if you look it up, it's hard to really find a definition of programming. It's not easy. So I try to come up with what I wanted to contrast traditional programming, intelligent programming. So I try to come up with the shortest kind of explanation. And the way I looked at it is traditional programming is think like a computer. In fact, you see these programming languages here in the slide. Many of you who are programmers, of course, know these. And what makes a computer programmer a good programmer is they know how a programming language works, and they can think in that programming language and write programs to do useful things. And how is that different than from intelligent programming? Well, we're going to change the game in programming. We're going to talk about thinking like a human. I'm claiming that intelligent programming requires you to think like a human. So it turns out that we have a computer programming language, even though it's 20 years old. It's now really coming into its own right now, and that language is NLP++. For the first time in computer science, we have a computer programming language that can write intelligent programs. NLP++, the conceptual grammar and visual text together make this technology's programming language. It's open source and runs with HPC systems on all three platforms. And somebody who worked in the company that first developed this said that this programming language allows anything thinkable. Again, you can think about it. How do people think? How do people do things? That's the crux of the intelligence part of the programming. So NLP++, as a game-changing computer language, it allows for concentrating on the intelligent task and not the programming itself. It automatically breaks text down into tokens. It handles all text, including Unicode and emojis. It has sophisticated rules and functions to construct syntactic trees from text. It's highly interconnected between text and knowledge, and that's the key. Knowledge and text are intimately woven in our brains, and that's why this is such a powerful computing language for intelligent programs. And it also has a built-in knowledge base called the conceptual grammar. The knowledge can be built on the fly while processing text. That's very important. For instance, if we're looking at text and it says Fred, and then later on in the text we say he, well, that he refers to Fred. And so we humans, as we process text, we are building knowledge in our brain of that text as we are reading it. So NLP++ can do that. And existing or new knowledge can be used for processing the text. And knowledge is hierarchical and can be tangled, and in effect, it can contain the conceptual grammar. You can build a knowledge base of all the knowledge in the world if you had enough time and space. And also there's a highly interconnected visual IDE which is visual text, which is written as a language extension in VS Code for rapid prototyping and development. It's very interesting that it's visual and that it's very difficult to program intelligent programs without some visual help. So we're going to be talking about the Clemson Radiology project, which is game-changing as well, because we're going to be trying to use this new game-changing technology. And of course, like I said, research in the university level, we're always looking to break new ground. And so it was interesting when we talked to a person who is a specialist in the area of radiology, when I had mentioned that the idea of human language is I have something in my brain and I spit out or say something or type something out that are words. Those words are then interpreted using all the rules and the world knowledge that the other person has to try to reconstruct in that other person's brain what the original person was trying to had in their thoughts and in their mind. So here we have an X-ray of an appendix. This person is saying the appendix wall is 4 millimeters thick, and that then gets interpreted by the other person, and they hopefully will construct the same kind of knowledge about that, what they're talking about in their brain. And that's what we're trying to do with NLP++ and language in general. So here's some radiology text. It is very hard. If you just start trying to read it, you're going to be lost probably by the second or third or fourth word. But what's the most important here is that we look at the radiology text and we have to understand this, imagine what the radiologists who wrote this had in their brain while they were writing it. And you're going to see it requires quite a lot of information. It's just not words. There's a lot of world knowledge that this person has. And you can see some of the highlighted phrases. Possible septations may be present. There's a dilatation of the pancreatic duct, anterior abnormal hernia. So these are things trying to understand this text and what this person's trying to say. Well, what are some of the things we need to understand text like that? Well, we need to know about the human body and their organs. We need to know measurements and observational attributes about organs, because radiologists talk about that, sizes, they see things, observational language that they use when they're making their text. There are normalities. They talk about things that are normal and abnormal. Sometimes it's just information. I'll show you something right after this slide about that. And we're trying to reconstruct again what's in the brain of the radiologist who wrote the text. So radiology in the NLP project, to give you an example of how knowledge would be used, here's some text. And in fact, this are the same thing written in 5 languages here, which are all saying that the appendix wall is 4 millimeters. 4 millimeters. And so you can see what our natural language processing system should get is that the organ is the appendix, the attribute we're looking at is the wall thickness, and the value we have that this person is seeing in the image, the radiology image, is that the wall thickness is 4 millimeters. And then in a language like NLP++, you can have the ability to have knowledge sitting in the system already there to which you can compare, so that you would be able to look at what was written there and compare it to the organ, the attribute, and see that normal is less than 3 millimeters, and that the 4 millimeters is greater than that. And then whatever you want your program to do, it will know. But the important thing is your program has understood what that radiologist has said. The information is put into a knowledge, a more structured knowledge of what that person said, and that then you can then compare it to world knowledge. Again, to be able to do this all in one language is really, really important. And it's one of the powers that we see in NLP++, and that why we are trying to use this newer technology that's trying to change the game on radiology. So I would like to introduce our next speaker. She is a team member, Amy Apon. She holds a PhD in computer science from Vanderbilt University. She was the director of the Arkansas High Performance Computing Center and professor of computing science from 1998 to 2011. She joined Clemson in 2011 as the chair of the Division of Computer Science. She was the director of the School of Computing from 2019 until this year. And now she is a professor of computer science and an active collaborator with the colleagues at HPC Systems, and uses HPCC Systems tools in both teaching and research.
David, thank you very much. And hello, everyone. As David said, my research group has been working with LexisNexis and HPCC Systems for several years. Each year, there are students funded to do research projects, and at least 5 students, advanced students, have been hired into LexisNexis from Clemson. Project areas have included systems work in HPCC Systems and machine learning across a number of different kinds of data problems. This year, we're doing our first project in natural language processing that does not include machine learning. NLP++ is new to the team, and we are evaluating which problem to tackle. A key feature of this approach, of the NLP++ approach, is that a large labeled data set is not needed to start the research. So we've dealt with this problem with industry partners in the past, where a partner wants us to analyze some kind of data set, but in fact, they can't really give us access to the data set because some part of the data is proprietary or protected in some way by the company. And so we end up getting a small data set that we can work with that has been sanitized, but it's difficult to apply large-scale machine learning techniques to a small data set. So we're excited that we can use a smaller sanitized data set as a starting point for our project in radiology and NLP++. So this project has 2 undergraduate students working on it with me. Ashton Williamson is a senior computer science major. He is passionate about NLP. His background includes study in linguistics. He lived in Spain and is fluent in Spanish as well as English. Dhruvisha Patel is a senior computer science major also. She is an energetic student with interest in computer security and NLP. She was originally from India, and her parents now live in the upstate of South Carolina. She speaks 5 languages. So I'll turn it over now to Ashton and let him tell you a little bit more about the steps we're taking in our project.
Thanks, Dr. Apon. So one of the challenges that we encountered in our research was how to incorporate existing medical knowledge into NLP++ in order to more effectively extract information from radiology reports. After investigating several options, we settled on a lexicon of radiology terms published by the Radiological Society of North America called Radlex. Radlex was created in 2006 by domain experts to standardize the vocabulary of radiology reports with the aim of facilitating computer interpretation. Radlex was chosen for 3 reasons. It's openly available, it's specific to the domain of radiology so as to limit extraneous information, and it's exhaustive in that it aims to supply a comprehensive list of terms included in radiology reports. On top of this, Radlex is a medical ontology, which means that in addition to providing standardized terms, it defines relationships between them. So after choosing an ontology, the next step was to get a better understanding of Radlex by performing some exploratory analysis. My first aim was to create a collapsible tree diagram to provide a more intuitive interface for navigating the ontology. Radlex has predefined parent-child relationships, thus creating a hierarchy which groups terms according to classes, for example, anatomical entities or imaging modalities. Since this was mainly implemented as a tool to explore the structure in terms of Radlex, I added a tooltip to display the definition of each term, if available, along with details about each subtree, including depth, the number of children, and number of descendants. So the next approach I took to understanding Radlex was to look at individual words in the terms and analyze how they occur across the lexicon. The first step here was generating a word cloud. Word clouds are simple visualizations, but can offer a lot of insight into large textual data sets. So here I created a word cloud of the 100 most common words in Radlex, filtering out the 100 most common English words, which are mostly prepositions and articles and give limited insight. Word frequency is mapped to font size so that larger words in the cloud correspond to more frequent appearance in the lexicon. The next step was to examine word distribution. I found that the median term length was 5 words, and terms ranged from 1 to 18 words in length, with the longest term being medial antebrachial cutaneous nerve component of trunk of anterior division of anterior ramus of left 8th cervical nerve. This, however, does not tell us anything about the distribution of words within the individual Radlex terms. To this end, I attempted to visualize the word co-occurrences or appearances in the same term as a network where each connection represented a co-occurrence and connection weights were determined by frequency of co-occurrence. In the graphic on the right, you can see a simplification of this concept in a single term. Note that only words from the top 100 list are being included in this network. So here we've extended the concept to the entire Radlex lexicon and created an interactive chord diagram. So as you can see, the outer labels correspond to the top 100 words ordered alphabetically, and the arc size corresponds to the total word count. Color gradient was added for visibility. Each co-occurrence is represented by a chord within the circle, and the weight of each chord is relative to its frequency. Take, for example, the term from the last slide, meningeal branch of left 7th cervical nerve. Notice that the word branch occurs before the word nerve. As it turns out, this is a common trend in the lexicon, which can be identified from examining the visualization. Note that the chord from branch to nerve is visibly wider at the intersection of the branch arc than the nerve arc. This is because branch more commonly precedes nerve in the Radlex terms than vice versa, by a factor of almost 75. As mentioned earlier, we are still in the preliminary stages of our research. One of the design challenges we face going forward is how best to incorporate Radlex into NLP++, and more generally, how to leverage the knowledge in the lexicon to better understand radiology reports. Some considerations in addressing this challenge include the design of knowledge bases to best accommodate our goals, as well as dealing with information outside the scope of Radlex, like non-standardized terms. Nevertheless, NLP++ has given us the toolkit to effectively tackle these challenges moving forward. Next, we're going to have Dhruvi talk a little bit about the literature, so I'll hand it over to her.
Thanks, Ashton. So I'll be talking about what we just went over and giving you a general idea and my experience about NLP, using NLP++. So talking about what is natural language processing. So natural language processing is a subfield of artificial intelligence, which is concerned with giving computers the ability to process text or spoken words, just as the same way human beings can. There are many applications of natural language processing, some of which are part of speech tagging. So part of speech tagging is the process of determining the part of speech of a particular word or phrase. For example, identifying make as a verb in I can make a paper plane, and as a noun in what make of a car do you own. Another application would be sentiment analysis. So attempting to identify qualities like attitude, emotion, confusion, etc. from text. Another application would be name entity recognition. So just identifying words or phrases as useful entities. For example, identifying Kentucky as a location or Fred as a man's name. So our research of analyzing radiology reports. So radiology reports presented today are generally in an unstructured format, which will make it difficult for radiologists or clinicians to read those and also provide proper follow-up treatments or medications to the patients. And in many cases, they can also miss any incidental finding, which may lead to fatal illness in patients. So we propose to use NLP++ to address this problem and also provide radiology reports in a structured or a flowsheet format, making it easier for radiologists or clinicians to provide proper follow-up treatments to the patients and also read those reports properly. NLP and radiology. So there have been many previous attempts to use NLP++ to study radiology reports, some of which were using text generation from images, machine learning to classify, identify, extraction, integrated existing packages. But for our project, we are using a completely integrated technology, which will incorporate linguistic and medical knowledge all in one system. So prior example of analyzing radiology reports. So I have a journal article here titled A General Natural Language Text Processor for Clinical Radiology, which was published in March of '94. The main objective of this paper was to process or identify clinical information presented in an unstructured format and map out the information into a structured format containing clinical terms. The main design included dividing the processor into 3 phases. The first phase was parsing, which identified the structure of text through the use of grammar. The second phase was regularization, which standardized the terms in the form of an initial target. And the third phase was encoding, which mapped the terms to a controlled vocabulary. So if talking about measurements and results, so in total, 230 radiology reports were identified and studied, and a panel of 3 physicians sat down to determine the recall and precision of the research. So they found out that without training specific to 4 diseases, the recall and precision of the system were up to 70% and 87%. So we can see from this article how precise NLP can be if we use it to study radiology reports. So the main difference between using the old research methods and our ongoing research, so the key difference is the past research did not have a knowledge base, whereas our ongoing research contains a knowledge base. Another major difference would be the output radiology reports, which were conducted in the old research, were not presented into a flow sheet format and were also not enough structured, whereas after processing our radiology reports, they're presented in a structured format. So our continuing work. So we are currently working with Dr. Alex Aving, who is a senior biostatistician and also a part of Prisma Data Support Core, to get those radiology reports or data that we can to work on. The main key point to notice here is our approach of using NLP++ does not require us to use many data sets, but only a few data sets to get started with. So that was my experience of working with NLP++ so far. I'm going to hand it back to Mr. Hilster.
Well, thanks, everyone. Thank you, Dhruvi, and everyone else. In summary here, the Clemson Radiology Project is game-changing in that we are trying to use a game-changing NLP technology and doing it in a way by looking at the research, finding out that, no, this has not been done in this way, and could this bring better solutions to the problem of NLP and radiology? And that's certainly our hope. And of course, though, we have many, many questions to answer. We are just in the beginning of this journey with this, not only this technology, but with radiology and this technology. What will ultimately be the task for this project? That's an important question we want to answer. This is pure research. Can NLP++ truly perform all the NLP tasks needed for the radiology project? This is a claim of the technology, and is that going to ring true? What knowledge from radiology open source will be useful and in what form? Ashton talked a little bit about that, and that's truly going to be a very interesting part of this project is how is this knowledge, how is it going to be organized? And not only that, how is it going to be organized so that we can understand text by radiologists? Also, will a small set of text really be sufficient for the scope of this project? One of the things that makes this possible is that when you are dealing with writing a program that understands the text, and we use human beings ourselves as programmers to look at the text and figure out what knowledge is being used and how the language is being used. We as human programmers and human beings can generalize. We don't have to go through training. We don't have to see a million things for us to understand that this could be said in many different ways, and we can understand the different ways because we know how, in this case, English is put together and how radiologists put together their phrases. So we have that ability to generalize while we are building the analyzer itself, and that allows us to do to take much fewer texts, and be able to write more generalized analyzers without that problem of having to have that immense amount of text which machine learning needs, and which is hard to get at, as Professor Apon talked about. Will the analyzer be proof of concept or more finished product? Are we going to show that it's possible to do this and that more work will be needed? Or are we going to be able to find some maybe lower hanging fruit and really come up something that's quite useful and maybe closer to production? Again, these are very interesting questions for this project. And will this, of course, generate publishable papers? Because one of the things that that the university always looks to do with students is to generate publishable papers on topics that have not been put out there as of yet. And that's why we saw Dhruvi looking at what has already been done with NLP and radiology. So as I said in the beginning, we have our lemmings jumping off, but we can maybe change this a little bit. We've already jumped, we've jumped together. We have the HPC systems and NLP++ helping guide us to processing radiology text. And now that we've taken the plunge, let's make the best of it together. And that's what HPCC Systems has been doing along with Clemson University. So I hope you enjoyed our talk today. And if you have any questions, we're here to answer them. Thank you so much.